So, where we just finish that one, that so this is understandable that VAC is equal to V angle. I mean, you just take 180 degree opposite, that is VCA, and it is VAC. This angle will be 30 degree. Just now I showed that this angle will be 30 degree, and is line to line voltage. So, this line to VAC is line to line voltage lagging from Vn by minus 30 degree. All these things are known, and line is untransposed, right. That means that is charge, expression of charge will become complex, right. So, now apply equation 5, again you have to go back to equation 5 and apply for line voltage, say VAB. So, VAB is equal to 1 upon 2 pi epsilon 0. Then I am not showing again the equation 5 already has been derived, just to apply that, right. Just to see that this thing, so just to see this configuration and you apply, right. So, it will be 1 upon 2 pi epsilon 0 QA ln d upon r plus QB ln r upon d plus QC ln d upon 2 d is equal to V angle 30 degree. This is equation 1, right, because VAB is equal to V angle 30 degree, right. Therefore, we are writing that it is equal to V angle 30, that means this expression is equal to V angle 30 degree. This is equation 1. Similarly, VAC, because we need VAC, because VAB plus VAC is equal to 3 VAN. So, VAC will be 1 upon 2 pi epsilon 0 QA ln 2 d upon r plus QB ln d upon d, that means this term will be eliminated, right, because this conductor when you are considering A to what you call VAC, A to C, right. So, this thing will come that QB ln, when you consider this QB, this is your conductor B, this side is D, this side is also D. So, that is why this will come QB ln d upon d, that means ln 1, that means this term will be vanished, it is 0, it will be 0, right. So, I will not put anywhere in the expression it is 0, but next later stage we will as this is 0 and accordingly we will evaluate, plus QC ln r upon 2 d is equal to V angle minus 30 degree, because VAC is equal to V angle minus 30 degree, that means VAC is equal to V angle minus 30 degree, right. Just now we have discussed that. So, this is equation 2. Now, QA plus QB plus QC is equal to 0, because it is a balanced system. Therefore, QB is equal to minus QA plus QC, right. This is equation 3. So, from equation 1 and 3, that means from equation 1 and equation 3, that means QB is equal to bracket minus bracket QA plus QC, you substitute here, you substitute that QB is equal to minus QA plus QC and simplify. If you do so, you will get 2 QA ln d upon r plus QC ln d upon 2 r is equal to 2 pi epsilon 0 into V angle minus 30 degree. This 2 pi epsilon cross multiplication. So, 2 pi epsilon 0 into V angle minus 30 degree. This is equation 4, right. Similarly, solving the next that means this expression is actually in terms of QA and QC. This expression also, this equation 2 also is a function of QA and QC, because this term is 0, this term is 0. That means, you solve equation 2 and equation 4, right. Therefore, if you solve equation 2 and equation 4, then our interest is only QA. Similarly, QC also you can solve for QC, but our interest to find out the charge, right. This is actually it is coulomb per meter, right. So, this if you solve for QA, it will be your 2 pi epsilon 0 V in bracket ln r upon d angle 30 degree minus ln d upon 2 r angle minus 30 degree divided by 2 into ln d upon r into ln r upon d minus ln 2 d upon r into ln r upon 2 d, this coulomb per meter, right. So, this that means this expression is a complex, because you have angle 30 degree here, angle minus 30 degree here, right, because line is untransposed, right. So, charging current of phase A IA is equal to omega into QA angle 90 degree, right. So, that means 2 pi f into QA angle minus angle 90 degree, because current is your charging current of phase A, that is why I am putting there is charging current of phase A. So, instead of IA I can put charging current say ICA, right, charging current of phase A omega into QA angle 90 degree. Actually Q is equal to in general CV, right. So, that means your directly you can write omega QA angle 90 degree, current charging current is leading, and this QA expression if you substitute, not putting it here, that is the expression of the your charging current ampere, right. So, if that means what, that if the line is untransposed, the charge actually coulomb per meter is a complex quantity, right. So, this is your what you call that expression. So, not very difficult one, just you have to understand little bit, and all these things we have tried to explain, right. So, next another example. So, this is your determine the line to line capacitance of a single phase line having the following arrangement of conductors. One circuit consists of 3 wires of 0.2 centimeter dia each, and the other circuit 2 wires of 0.4 centimeter dia each, right. After this example, we will stop the capacitance one, right. So, this is the last example for capacitance one. So, this is for inductance case we have solved this in this composite conductor X, 3 conductors are here, and here M is equal to your what you call 3, and here N is equal to 2 conductors are there, right. Therefore, first you find out DEQ, that is all the mutual distances. So, 3 conductors here, 2 are here, 3 into 2 Mn is equal to 6. I have written to the power 1 upon Mn. So, dA dash, dAb dash, dBa dash, dBb dash, dCa dash, dCb dash, right. So, all these distances here, all the things I have shown you, all 4 meter is given, this is 6 meter is given, this 4 meter is given, all other distances you can easily compute. I have directly written, but this you can easily make it, right. So, it is 6 into 7.211 into 7.211 into 6 into 10 into 7.211 to the power 1 upon 6. It will come 7.162 meter, right. Similarly, Rx, the group X, right, all the radius your diameter same 0.2 for this one. So, radius will be 0.2 by 2, that is 0.001 meter. Similarly, here also this group radius is diameter is 0.4 centimeter. So, R is equal to 0.4 by 2 is equal to 0.2 centimeter is equal to 0.002 meter, right. Therefore, find out the your self one with the self GMD one for this group, right. Therefore, DSX, DAA, DAB, DAC, DBA, DBB, DBC, DCA, DCB, DCC, DAA, DBB and DCC actually is equal to Rx, and all the 9 possibilities 3 into 3. So, to the power 1 upon 9, right. So, you can easily calculate this your DSX. So, it is 0.001 cube into 0.4 to the power 4 into E square to the power 1 by 9. So, 0.294 meter, right. Similarly, DSY is equal to your dA dash A dash into dA dash B dash to the power half, whatever it comes 0.0894 meter. So, now again apply equation 7, whatever has been derived, right, and Cxy pi epsilon 0 ln dEq upon root over dsx into dsy farad per meter. So, substitute all these values for dEq, dsx, dsy, you will get Cxy is equal to 0.00734 microfarad per kilometer, right. So, with this the capacitance calculation of transmission line now it is over, but when we will come to the your characteristic or performance of 3 phase transmission line, at that time we will see again this charging capacitance, right, and its effect. So, next one, so this capacitance one is over, right. Next one will be that power system, your power unit system will start, right. So, power system component and power unit system. So, here generally you have seen when you are drawing the diagram for power system network, right. So, power system component and power unit system, that basically we are making single line diagram, right. Although it is a 3 phase system, because 3 phase is your 3 phase system is basically a balanced system. So, and that is why it can be represented by your single line diagram. And another thing is that but if system is unbalanced, then you have to consider the mutual coupling between the conductors as well as between the conductor and your neutral, right. I mean, I would make it like that, that between the phases you have to all the mutual phase conductors as well as phase to neutral conductors, you have to consider the mutual inductance if system is unbalanced, particularly for the transmission line, that each phase is carrying almost the same power. It is a balanced system, voltage is also balanced, but when you come to distribution system, say 11 kV system, in our country mostly it is 11 kV system. So, your distribution system, in that case, that each your loads are not balanced, some cases it is unbalanced, and in that case you have to consider the your what you call that your mutual inductances. In that case, those things cannot be represented by a single line diagram, right. You have to consider all the three phases. So, power system components. So, for transmission system we will go for this thing single line diagram, we will come later. So, a complete circuit diagram of power system, that is why I have written something for all the three phases is very complicated, because you have A, B, C 3 phases and different components are there like synchronous generator, then transformers, right, circuit breakers, right, and if many other devices like shunt capacitors, reactors or fax devices, and then your what you call then your and all other things, all the your what you call components, if you put it together it looks very complicated, right. So, it is very much practical to represent a power system using simple your symbols for each component, resulting in what is called a single line diagram, right. So, that is why the power system engineers has devised the power unit system such that different physical quantities such as current, voltage, power and impedance are expressed as a decimal fraction or multiple of base quantities, right. So, in this system the different voltage level disappear. When you go for power unit system, you will find it is all the quantities will be given as a dimensionless quantities. So, voltage level will disappear and it will, and power network consisting of synchronous generator, transformers and line reduces to simple impedances, right. So, this is the major advantage of power unit system, right. Once you transform everything in power unit system, then things will be easier, but before that you have to understand actually how to convert the power unit system for one base to another. So, sometimes students they make some silly mistakes for power unit system, right, to conversion. So, let us see how we can make it. First thing, so let us start like this, right. Say single phase representation of a balanced 3 phase system. Suppose this one, for example, suppose this was a 3 phase supply system, right. So, simple thing, right. So, this is say this is your synchronous generator, for example. So, this is phase A, this is phase B and this is phase C voltages, right, and impedance is given say ZG stands for impedance of the generator, synchronous generator say, right, and this is the 3 phase load star connected, right, and impedance of the this one ZL, that is a balanced system. So, it is a neutral to neutral is connected, but as it is a balanced system, so no current is flowing through the neutral. Therefore, this neutral impedance here to here Zn will have no effect, right, as long as it is balanced system, but in reality actually nothing is completely ideal, right. So, it cannot completely balance, but it is balanced, right. That means, in this case this is a balanced 3 phase. In this case, rather than as it is a balance and all the phases phase A, phase B and phase C carrying equal power, that means equal current, right. So, that means each one, instead of considering all the 3 phases, we can consider only one phase. So, that is why only one phase is drawn, because neutral is not carrying any current 0. So, Zn has no effect. So, in that case your EA, that your voltage of the phase A is Zg will be there, this one, and this is ZL, and ultimately your what you call that expression of your phase A, that is equivalent circuit diagram of the phase A, right. So, that means that rather than 3 phase, we can represent it by your single phase circuit. That means, EA is equal to, if you apply KVL in this equation, it will be basically your Zg plus ZL into IA is equal to EA. That means, EA is equal to Zg into IA, your Zg plus ZL into IA, right. So, this is a single phase representation of balanced 3 phase network of figure 1, right. That means, this from circuit theory also, 3 phase circuit analysis also you have studied this kind of diagram, right. That means, that is your figure 1. I have explained everything. So, figure 1 that means this figure, this is figure 1 and this is figure 2. That means, figure 1 shows a simple balanced 3 phase network. As the network is balanced, the neutral impedance I told you Zn does not affect the behavior of the network. Therefore, from the for the reference phase A, that is figure 2, we can write A is equal to Zg plus Zl into I. This is equation 1, right. So, this is a new topic. So, again starting from equation 1 and figure 2, that means this one gives the single phase equivalent. So, figure 2 is the single phase equivalent of a balanced 3 phase network of figure 1. As the system is balanced, the voltage and system is balanced, that means voltage and current in other phases only have the same magnitude, but phase shifting will be 120 degree, right. Yeah, as you know, if you take one is reference, then another will be 120 degree, minus 120 and minus 140 240, right, the way you want. So, but magnitude will remain same, only that phase difference will be different. Now, for a transformer, now we will come to the transformer. This is very important thing, many things here you have to understand. As far as your knowledge is concerned, things are very simplified. Basically, that your 3 phase transformer is 3 phase power is transformed by use of 3 phase units, right. Particularly for high voltage, extra high voltage system, that rating of the transformer is very high, right. In that case, if you try to design a 3 phase transformer, then it occupies actually a huge volume and insulation problem also, right. That is why what they do, they take 3 phase single phase transformer, right, and after that they connect it in 3 phases. The advantage, major advantage is that first thing is the insulation clearances, second thing is that your transportation. Suppose if you design in a single unit as a 3 phase transformer, its volume will be heavy and very difficult to carry it as a shipping problem or transportation problem. That is why for large power transformer, they take 3 single phase transformer and they connect it 3 single phase in 3 phase, such that it should be 3 phase. Another advantage of such connection is that, suppose if you take one unit, because 3 single phase are there, they are making it as 3 phase. If one unit is taking as a, as a repair, but other 2 phase also you can operate, but rating has, but it has to be derated, and the rating will be approximately 57.7, that is 1 upon root 3, that is 58.8%. Those things for the machine courses, not here, but that is called V connection. But in this case, generally transformer you have star or delta, right. So, 4 combinations will be there, a star star, this is a star star, right. This convention I have taken from American Standard Association, right, but anything you can take, but accordingly you have to follow. This is star star connection, star star neutral is available, right. For delta delta neutral is not available, right, and star case delta delta case line voltage and phase voltage same, whereas star case line voltage is equal to root 3 times the phase voltage, and star delta and delta star. So, altogether 4 such combinations are there, and all these 4 combinations are you have to use, mostly used are these 2, and other 2 why not, we will come to that, right. So, this is the schematic diagram. Later with putting its each winding, that winding now turns and other thing will come later, but this is star star, delta delta, star delta, delta star, these 4 combinations are there, right, for the transformer. Now, the 3 phase power is transformed by use of, I told you, 3 phase units. However, in large extra high voltage units, the insulation clearances and shipping limitation may require a bank of 3 single phase transformer connected in 3 phase arrangement. That means, 3 single phase transformer will be connected in 3 phase, such that transportation is problem. Suppose transfer will be easier. Suppose manufacturer manufactures this somewhere, and you are carrying some 1000 kilometers to some other place. So, if transformer is made for 3 phase together a single unit is very difficult to carry, because the volume will be huge, but if you make single phase one and connect it, then transportation is easier, right. So, primary and secondary windings can be connected in either star or delta, right, configuration. This result in 4 possible combination of connections that I showed you, the star star, delta delta, star delta and delta star, right, as is shown by your figure 3. That means, this one I have shown you all these combinations, right. Now, star star, it actually offers advantages of decreased insulation and your insulation cost and the availability of the neutral for grounding purposes. For its decreased insulation cost means that for star star, that your A to N, B to N or C to N, that your each winding when you design, that only that phase voltage is impressed on the winding, not the line to line voltage, it is line to neutral voltage. That is why insulation cost will be less, right. So, and the grounding facility for star connection, it is there, right. However, because of the your problem associated with third harmonics and unbalanced operation, this connection is rarely used, right, but there is no path for third harmonic current circulation for the star star connection, right, and for unbalanced operation, right. So, in that case, that is why the star star connection is rarely used. So, to make this, that means star star connection will be there, but not much in use as a your high voltage your transmission system, right. Now, although we will not study, but for purpose of your some ideas, to eliminate the harmonics, a third set of winding called a tertiary winding connected in delta is normally fitted on the core to provide a part of the third harmonic current. That means, a third your set of windings called your tertiary winding, and that will be delta connected, is normally fitted on the core to provide a path for the third harmonic currents, right. This is known as 3 winding transformers. So, but although we will not study here 3 winding transformers, but in laboratory many of you might have done experiments on these 3 winding transformers. So, the tertiary winding, it can be loaded with either your switch reactors or capacitors for reactive power compensation, right. Although we will not study here, but this tertiary winding is this thing, your many cases in your institute or in your engineering in your colleges, that laboratories, these 3 winding transformers are there, right. Particularly short circuit, to determine the parameters of 3 winding transformers using short circuit and open circuit test, right. So, now come to delta delta. Delta delta actually it provides no neutral connection. For delta delta there is no neutral connection, and each transformer must withstand full line to line voltage, because for the delta connection, for each phase the winding is there, it will be full voltage will be impressed, because delta line and phase voltage they are same, line to line and phase voltage same. So, full voltage will be your to withstand full line to line voltage, right. Therefore, the delta connection does, however, provide a path for third harmonic currents to flow. Delta will, because it is a delta connection, so it provides a path for third harmonic currents to flow. This connection has the advantage that one transformer, if you can take it for repair, right, then your other two, I mean if delta delta, if one winding you, because 3 single unit we are connecting, it is not a single 3 phase unit, 3 single phase unit we are connecting as a 3 phase. If one unit is taking out, if one is taking out, it will be, we call V connection, right, or open delta connection, right. In that case, it still can, but the rating has to be, it has to be derated, but still it is 57.7, approximately 58% of the original bank it can supply, right. 3 phase power at least 58% of its rated value, and this is known as V connection or open delta connection, right. But the most common connection is the star delta or delta star, right. But this connection is more stable with respect to the unbalanced load, and if the Y connection is used on the high voltage side, insulation costs are reduced. Just basically for star delta transformer or delta star transformer, the star side basically used for the high voltage, basically this side will be high voltage side. That means, when you are using that a step down transformer, the primary side should be high voltage and this side should be low voltage, and we will go for a step up, then this side should be low voltage, this side should be high voltage, right. So, I hope you have understood this, right. So, for start delta or delta star very common, because delta side kept under your high voltage side, because each phase that voltage actually will be the phase voltage will be induced. So, insulation cost will be less, right. So, and for the step down transformer, suppose 220 by 132 kV, right. So, this side actually it should be high voltage side and this should be low voltage side, and if you step up, so this side suppose for example 33 to 220 kV for example say. So, this side will be low voltage side, this side should be high voltage side. So, start delta or delta star side should be always at the high voltage side and delta should be always low voltage side. I hope this part you have understood, right. So, therefore, the start delta connection is commonly used to step down, just now I told a high voltage to a lower voltage, just now I have told everything. The neutral point on the high voltage side can be grounded, this is desirable in most cases. Here it is not shown, for star side neutral point will be grounded, this side also will be grounded, although no diagram I have shown it here, but later we will show, right. So, neutral will be grounded, and when we will study the fault studies another thing, at that time we will see about all this, right. So, neutral side of the star should be grounded, here also it should be grounded, right, and this is desirable in most cases. And same thing for delta star, I told everything, right. For delta star, this connection is commonly used for stepping up to up to a high voltage, this is also I have told you, right. So, that means start delta or delta star side should be always on the high voltage side. If you go for a step down transformer, you start delta connection. If you go for step up transformer for power transmission system, then it will be delta star, right. So, the per phase model of a 3-phase transformer. Now, we have to see for per phase model, and here you have to understand a lot, right. So, in star or delta connection, the ratio of the voltage on high voltage and low voltage side are the same as the ratio of the phase voltage on the high voltage and low voltage side. If you take very simple it is, if you take star or delta connection, you can draw yourself. So, ratio of the line voltage on high voltage and low voltage side are the same, right, because are the same as the ratio of the phase voltage on the high voltage and low voltage side, because in star the ratio of the voltage on the high voltage and low voltage, because star case that your what you call that line voltage is equal to root 3 times phase voltage, and for the delta case line voltage and phase voltage both are same. So, that is why the ratio of the phase voltage on the HV and LV side they are same. You can do it because you have studied also machine, right, electrical machine. Furthermore, there is no phase shift between the corresponding line voltage on the high voltage and low voltage side. For star connection and delta connection, there is no phase shift between the corresponding line voltage on the high voltage side and the low voltage side. Look, I am not using any primary or secondary, I am already talking about the high voltage and low voltage, right. So, no phase shift for star or delta, right, between the corresponding line voltage on the high voltage side and low voltage side, right. However, star delta and delta star connection will result in a phase shift of 30 degree. That means, star delta or delta star, their connection will result in a phase shift of 30 degree between the primary and secondary line to line voltage. Now, I am coming to between primary and secondary line to line your what you call voltage, right, between the primary and secondary line to line voltage. For example, this is for example, you take star delta connection, right. Consider the star delta schematic diagram of figure 3. That means, this diagram just now we have seen this diagram, right, this one star delta, right. So, in this case your this side star side actually capital ABC and delta side small ABC. Delta is line and phase voltage same, right. So, delta, if you draw the phasor, this is delta side VAB, VBC, VCA 120 degree apart, not shown, but you know that is from balance 120 degree. And for the star side, right, for the star side that VAN is taken as a reference. So, this is my VAN then VBN and this VCN all are 120 degree apart. So, this is VBN. So, take VNB just 180 degree. So, just opposite. So, this is VNB, that means this is my VNB, right. That means this is, then you make this, complete this is VAB. So, VAB is equal to VAN plus VNB, right. So, this is my VAB. So, that means this angle is 30 degree, that means this is VAN, but this VAB is 30 degree. Now, if you put, if I make this one, if I make this one here, if I make this VAB here, suppose this is my VAB, then this angle is 30 degree. That means this star side line voltage leading the delta side line voltage by angle 30 degree. This is delta side line to line voltage and this is star side line to line voltage VAB. So, V capital A capital B, right. So, VAB is leading VAB 30 degree. That means, for star delta or delta star, there will be a phase shift of 30 degree. Got it? No? Thank you.